Hello dear students, in this video today I am going to show you a two-step solution for a very tough problem from Pathfinder. So let us go to it. So let us first have a look at the question. A uniform hollow cylinder of mass m rests on a wedge of mass capital M. So this is a hollow cylinder, it rests on a wedge of mass capital M. This wedge is held on a frictionless slope of inclination theta as shown in the figure. So this wedge is held on this slope. This is a frictionless slope. Friction between the cylinder and the top surface of the wedge is sufficient to prevent sliding. So basically he's saying us when the motion is going on, there is no slipping between the cylinder and the surface here. Find the acceleration of the wedge after it is released. So just after this system is released, what is the acceleration of this wedge? Okay, so let us have a look at the animation here. Okay. So you can see the wedge sliding down and the cylinder is pure rolling on top of the wedge. Okay, now let us go on to the, so I'll take up two solutions. The first is the standard solution that we generally do. Then I'll take up the awesome two-step solution. So let us move on to the standard solution. Okay, so this is the standard solution which we have. In this solution, we draw the free body diagram of the wedge. Okay, write the normal reaction force mg, mark the acceleration, write the friction, write the equation, and write net force along this direction into equals mass into acceleration. For the cylinder on top, we take the motion of cylinder with respect to the wedge, right? So draw the pseudo force, write the normal, friction, and all this. After that, we write the force equation, we write the torque equation, we write the no slip condition. We solve all these equations, and finally, yes, we do get the answer. Okay, let us move on to the two-step solution now. Awesome solution. Okay, so let us go on to the solution now. Okay, see in this solution, no, the first thing is I'm going to take this both the cylinder and the wedge as a system. So on the cylinder and the wedge, the net force in this direction will be M plus M into G sine theta. Okay, this is the net force on this in this direction. Next, the acceleration of this wedge is, let us take it as this as A downward. Okay, the acceleration of this wedge is A downward. The acceleration of the cylinder with respect to the wedge is in this direction, and so we'll just write this as A dash in this direction. Okay, so for this whole system, I'm going to write the equation. So let's see this. So in this direction, the equation would be M plus M into G sine theta equal to mass of the wedge. What is the mass of the wedge? Wedge has a mass capital M, this has a mass small m. Okay, so M into A plus M into, see the total force on this direction equal to the acceleration M into A in this direction and mass of cylinder into component of acceleration of the cylinder in this direction. So what does that tell me? So that will be M into, so if I resolve this into two components, this A dash into two components, we'll have this as A dash cos theta, and in this direction we'll have this as A dash sin theta. Okay, so in this direction the acceleration of this is A minus A dash cos theta. This is the first equation. Okay. Let us move on to the second equation for the cylinder. Okay. So I'm going to write here FBD of cylinder in frame of wedge. Okay, FBD of cylinder in frame of wedge. So let us draw the cylinder. Okay, the forces acting on the cylinder are, one is the pseudo force, which is mass into acceleration, the gravitational force m into g, normal reaction force n. Okay, there is a friction force also. Which direction is friction, we are not going to go to it. I'm just going to mark some direction. Okay, and the acceleration of this with respect to the wedges in this direction, which is A dash. Okay, now what I'm going to write here is, I'm going to write the torque about O. So torque about O, torque about O on the cylinder or on the cylinder. Okay, and this will be what, tell me? The torque due to this friction is 0, the torque due to normal is 0, okay, torque due to mg is 0, the torque due to ma, so this side is this is theta, so this is theta, so ma sin theta, the torque is 0 because it is passing through this point. There will be a torque due to ma cos theta. So I'll write here ma cos theta into r equal to ma cos theta into r equal to the moment of inertia about this point. The moment of inertia about this point is 2 mr square into alpha. Okay, the angular acceleration is alpha. I can write the angular acceleration as directly A dash by r. This is our second equation. Okay. So we just have two equations and two variables. You see, the variables are only A dash and A. Now, if I can put the value of A dash from here. So what is A dash here? Tell me. I'll just strike out this and M here, and A dash equal to R also we can cancel out. A cos theta by okay. A dash equal to A cos theta by 2. If I just keep my A dash equal to A cos theta by 2 here, in just 2 steps, I have got the answer. So see, the advantage of this method is we have eliminated the friction force completely, we have eliminated the normal reaction completely. In the previous method, we had taken 5 steps, okay, and lots of calculations. There could be a lot of chance of silly mistakes, but in this method, just 2 steps. Awesome solution, superb solution, and this method will get you to the top. See you all in the next video.